Welcome to the third lecture on quantum computing. In the first two lectures, we briefly talked about which applications you can run on a quantum computer, where quantum computers may be useful and why. But we will go into more details with the why now and how. So for this, we'll dive into the fundamental mathematics of quantum computing, which is mostly linear algebra, and we'll go into more detail in the next and the lecture after the next lecture. And we'll learn about the differences between classical and quantum computers by looking at classical probabilistic systems and quantum computers. And quantum computers are always probabilistic systems, so that's one important feature of quantum computers. We will learn more about that in a bit. Quantum theory, as we mentioned previously already, is often presented as an abstruse and very difficult theory. And physicists like Richard Feynman contributed to that notion. Richard Feynman, the famous Nobel Prize winner, and the guy who kicked off the whole field, even he contributed to that by saying things like, whoever claims to have understood quantum theory has not understood quantum theory. Um, I don't think that this is the case. I think quantum theory is just very different to the classical experiences in our macroscopic world. Still, everything in our world is based on quantum theory, everything in our universe. So it's the most fundamental language of the universe, as we already mentioned at the very beginning of this course. So it is just different. And this is what you just have to keep in mind. Keep an open mind, and even if things look strange, this may just be quantum behavior. So we'll learn about some new features, or some of you will learn about some new features of nature. And for others, it may already be familiar depending on your background. But still, the subset of quantum theory that we need in order to write software for quantum computers, I'm not talking about building quantum computers, that's a different story, but the subset that we need to write software, it's very small, so even better. And as I said, for computer scientists, if we look at it from a computer science perspective, you can say that quantum theory is the most fundamental language of the universe, the machine language of the universe, and everything else sits on top of quantum theory. And all programs about the evolution of the universe are written in the lowest level language known as quantum theory. And here too, if we talk about programs that run on quantum computers, we talk about evolution. So we take a well-defined initial state that we understand, and then we evolve this state by applying gates in terms of a gate model chip. And in the end, hopefully get a result that's useful, something that tells us something useful about our problem, or even provides us with a solution to the problem we intend to solve. So let's put this again in more concrete terms, and I think we mentioned that at the beginning already. We have these four forces: electromagnetic force, weak force, strong force, and gravity. And for the first three, we have a quantum theory in place. For the fourth one, we don't have one right now, but I'm sure at some point someone will come up with a solution to that problem. And we briefly talked about the difficulties as to why this is, but this shall not consider us here in that course. I think we had that one at the beginning too. So in physics, you don't like to call these higher level languages. So the forces, you don't like to call these higher level languages. So you have different names for them, like quantum electrodynamics, quantum chromodynamics. And the programs that we set up are these initial conditions, fields and forces and such, with the particles and certain configurations. And what we do in quantum computing, that's the particularly exciting thing is sort of we hack into the universe and run our program on the most fundamental aspect of the universe, the machine language of the universe. So quantum theory comes with a couple of postulates, four specifically. And we'll look at these four postulates in order to understand how quantum computers work better. After that, we look at how quantum computers leverage these four postulates. Okay? So this first postulate that we have is that every quantum system is described completely by state vector. All properties of the system can be deduced from the state vector. So that means every quantum system exists in its own state space. Quantum states are equivalent to positions in that space. In case of quantum theory, that space is complex. That is just how nature is given it to us. So we use complex numbers to describe the probability amplitudes associated with each of the states. So say you have a quantum system. Let me go back here. And it can represent a state. So let's call it state psi. And that state psi, it has two configurations. It has possible states 0 and 1. So what you see here is both states in a superposition. So in the end, when you measure that system, when you look at it, it will take one of these two states here. But right now it's an equally distributed superposition. So with half of the probability, remember you have to square the probability amplitudes to get the probabilities. Half the probability of collapsing into 0 and half the probability of collapsing into 1 when you look at that system. Okay. And positions in the space are described in terms of the basis states. So if we go back here, the basis states in that simple case with one qubit, that would be the basis states. So these two, 0 and 1. And they have usually a vectorial representation. So this is just a name that you give to a vector. So that's the bracket notation. You remember we briefly mentioned that last time. But if we look at the state 0, then it is given by the vector 1, 0. And if we look at the state 1, then it is given by 0, 1. Okay. Something else that you will see sometimes is that we express the vectors in that space by probability amplitudes. So since we have 1/2 probability here of this state collapsing either into 0 or 1, you could say I associate this 1 over square root of 2 with my first state, with 0, and with my second state, with 1, right? So this is how you sometimes, or most of the time, represent your state in terms of the probability amplitudes. But we'll look at that in more detail briefly. Okay. So what we use is the so-called Dirac notation to describe these quantum states. It's also called bracket notation. If you see it with this arrow to the right here, so psi with arrow to the right here, or the bracket to the right, then we call this ket. If you see it with the arrow to the left, we call it a bra. So a state vector is a weighted sum of basis states. So if we look at that, just as we had it right now with 0 and 1, this is just a sum of more different states. So assume you have a multiple qubit system. In an example, you have 3. Then what you could say the first one is 0, 0, 0. The second one is 1, 0, 0, etc. and so on. And this is just a combination of the possible states. Associated with each of the states, you see a probability amplitude. So all in all, these probability amplitudes for n states, so you have n states here, these probability amplitudes, the squared amplitudes, must sum to unity. That's one of the conditions, because it's probabilities that we're talking about, so it can't sum to 1.2 or even more or less. It must always be 1, so they must sum to unity. The basis states allow us to describe any point in the state space of the system. And as I just said before, we'll often write the state as a vector of the coefficients. Okay? Let's look at the second postulate. The probability of a measurement on a quantum system giving a certain result is determined by the weight of the relevant basis state in the state vector. After the measurement, the system is in the state corresponding to the result of the measurement. So consider that state psi here with probability amplitudes a sub 0 and a sub 1. So the example that we used before was just an equally weighted superposition. So I will, as an example, just write down a sub 0 is 1.5 or 1 over square root of 2. And a sub 1 in the case that we had before was also 1 over the square root of 2. Okay, but these are just examples. So it could be anything given the condition that both squared sum to unity. A measurement of the state can only yield two possible results here. So it can be 0 or 1. So remember, this state here is a superposition of possible states, each one associated with a probability amplitude. But as nature has given it to us, anytime you look at a quantum system closely, anytime you measure it, then it will collapse. It will collapse into one definite state. So in that case, it may either collapse into 1, 0, or it will collapse into 0, 1. Because this one here is 0, the state 0, this one is the state 1. So that means all the rich information contained in a superposition will be lost when you measure the system. So once you measure the system, you better be sure that your computation is complete. So we will see later on that this is also a challenge when we do computations. We don't want to interfere with the system too much, because if we do that, it will collapse before we finished our computation, which is a serious problem, because in the worst case, we didn't learn anything about our problem, or we didn't get a solution to our problem. That's not what we want. The outcome is probabilistic. So what you see here, squared, that means, because we're dealing with complex numbers really, here you have this a sub 0 with a star, the superscript, and that is the complex conjugate. Okay, so if we talk about complex numbers, and say we have a complex number z here, and we say the complex number c has a real part a plus bi, then the complex conjugate z star equals a minus bi. So it means that we just switch the sign of the complex part. Okay, and that's what happens here. So if we multiply that out, then we get the probability. So probability amplitude to the probability. Okay, that's what we mean when we say square the probability. And the normalization condition must hold, which is what we just said before. The amplitudes, the squared amplitudes, must sum to unity. The post-measurement state, that's the result that you get. So imagine you have a problem that comes with 10 solutions. And these 10 solutions, they exist in this rich superposition. Each of these possible solutions associated with a certain probability amplitude. Not necessarily equally weighted, can be anything. By the way, this is the whole artistry of quantum computing. So on the one hand, of course, representing these states, and on the other hand, manipulating the probability amplitude such that once you measure the system, once you look at it, you get the result that tells you something about your problem or is the solution to your problem. So, and that's very challenging sometimes, as we will see. So after the measurement, the state of the system is the state associated with the result of the measurements. And if the result of the measurement is 1, then the state of the qubit after the measurement is 1. So an example state, as we have here, so which is not an equally weighted superposition. So we have 1 over the square root of 3 for the state 0, and we have the square root of 2/3 associated with the state 1. So if we write that down differently in terms of the amplitudes, so if we just have the vector, say 1 over the square root of 3, and we say 2/3, and that square root. So this is how you would represent the probability amplitudes in a vectorial form. So this is exactly the same state as you see here. Okay. So if we now square that 1, so square 1 over the square root of 3 is 1/3. So if the result is 0, then the state of the qubit after a measurement equals 0. And now for the second one, if we square that one, it's 2/3. So if the result is 1, then the state of the qubit after the measurement is psi for state 1. So there's a higher probability, a higher chance to end up with this state, with the second one, because the probability amplitude is higher. But that doesn't mean that you'll always get it. That's a very important thing in quantum computing too. So even if you do everything right, even if your algorithm is correct, you still may end up with a solution that's not your favorable solution. So that is not the solution to your problem. That's why you don't only do measurement once. So you measure a you measure the state after doing your computation a couple times. So you read it out maybe 1,000 times. And if you have 800 times an identical solution and 200 times something else, then most likely the solution that you measure 800 times before is the right solution to your problem, if you implemented your algorithm correctly, of course. And some cautionary remarks here. The change of state following a measurement, sometimes called the collapse of the wave function. This is the Copenhagen interpretation of quantum mechanics that also says as long as I don't look at a system, the physical reality does not exist. So looking at the system creates the physical reality, meaning it's just a statistical thing. So until I measure that system, let's say I have a 1-qubit system, which is with some probability amplitudes associated with the state 0 and associated with the state 1, only when you look at that system and get a definite result, which is either 0 or 1, only then I have my physical reality. So the immediate remeasurement must give the same answer to that. The order of measurements of complicated quantum system is also important. So the sequence in which you execute your measurements matters and can influence the results, which we will also learn about more in a couple lectures. The measurements in quantum mechanics are represented by Hermitian operators. So if we look at that, you have matrices, and here we have the matrix M sub ij, which equals the complex conjugate of transpose of mji. Okay, so if you switch the sign and look at where you find mij in the complex conjugate matrix, it's mji. So we'll learn about that more. So it's the transpose that matters. So you may have seen the dagger before, dagger notation, which is just a complex conjugate transpose of your matrix. If for two Hermitian operators P and Q, we see PQ minus QP equals 0, then the operators are set to commute. And the order of measurement doesn't matter. So remember that your operators, your gates, whatever you apply to your quantum state are matrices or mathematically represented by matrices. So it's important to consider the sequence of application of these gates. And if you get 0 here, then the sequence doesn't matter. And the operators commute. On the other hand, if they do not commute, then the order matters. So it's, let's say you have these two operators here, and you apply P and then Q to your state, will not get the same result as if applying Q and then P to your state. That's important to keep in mind. The third postulate is the evolution of a closed quantum system is described by unitary transformation. So first, we recall that our quantum system can be described by a state vector, which for a single qubit can be written as we did before, with the amplitudes here, a sub 0, a sub 1, which is the same really as writing it that way here. A sub 0 associated with the state 0, a sub 1 associated with the state 1. And so we do something to the qubit. Imagine that. We apply some transformation to it, and the state, so the evolution of the state, results in a sub 0 prime and a sub 1 prime. Okay, you have different amplitudes. Still the same basis vectors that you have. This didn't change anything with the basis vectors, but it changed the probability amplitudes associated with each of the basis vectors. And how you apply such a transformation is the question now. So you do apply unitary transformations, so represented by matrices, Hermitian matrices, where U is some kind of operator here in that case. So in that case, we get to a new state, which means different probability amplitudes by applying the operator U here. In our vector-based representation of quantum mechanics, U can be represented as a matrix. Yeah, we had that before. And by combining two matrices, let's say we recall the laws of matrix multiplication, the matrix of size m times n multiplied by a matrix of size n times p gives a matrix of size m times p. Okay, if we look at that more concretely, so here m and n equals 2, and p equals 1 because we only have a 1 qubit state. So remember the state that we looked at before, could also write it as a sub 0, 1, 0 plus a sub 1, 0, 1. Okay, so that means we have 1 qubit that we operate on here. And we operate on that with the operator U. And after applying the operator U, we end up with new probability amplitudes. So what it really is the application of U11 applied to, or U sub 11 applied to A sub 0, and U12 applied to A sub 1 for the state A sub 0 prime. So that's what you end up here, what you end up with here. Okay, and the same here for A sub 1 prime, where you have U21 applied to A sub 0 and U22 applied to A sub 1. And we can try that out with a very simple example. Let's say we have the NOT matrix, so the NOT gate, which transforms the state 0 to the state 1 and vice versa. So let's say we apply that to the state 1, 0, then the result will be 0 times 1 plus 1 times 0 equals 0, and we have 1 times 1 plus 0 times 0 is 1. Okay, so you transformed the state 0 here to the state 1 here. And it's also important that these operators are reversible. So apply it twice and you will get back the original state. Here we have the NOT example again, the classical NOT gate that you see here. What it does is it changes the state 0 to 1, changes the state 1 to 0, and the analog of that, as we just had in the example, is for our vectorial representation, where we start with 1, 0 to change it to 0, 1. And we'll represent it as a matrix, as we just did before, and it must hold for all amplitudes of A sub 0, A sub 1, so all the values. And the matrix NOT is represented by X, so the letter X that you will see quite often. So you could write that down in bracket notation. X on the state 0 is the same as 0, 1, 1, 0, to that state. Okay. And one condition is unitarity, so we cannot use any transformation that we like. Only unitary transformations are permitted. So what you see here is unitary transformation satisfies the condition of u dagger times u equals I. So that means the complex conjugate transpose is this one here, so the dagger notation that you see quite often in quantum physics. That one takes the complex conjugate of a matrix, which means switching the signs of each complex number that you find in that matrix, and then you do the transposition matrix. Okay, and if you execute that, then the result must be identity. So let's look at the knot transformation. We don't have any complex numbers in the knot transformation here, but let's see. If we look at that transformation, so the complex conjugate transpose is the same as the original knot transformation. And now if we execute that multiplication here, we end up with identity. As you know, the identity transformation just leaves a state alone. So you may wonder, why do I need an identity transformation? Can't I just leave any state alone? That becomes important when I operate on multiple qubits, and we'll look at that in a moment. But just to say that much, let's say I have a 2-qubit state, like that one here, and I want to flip the first one, but leave the second one alone. Then how you do it is you apply the knot transformation to the first one and leave the second alone by applying the identity transformation to it. And that is done by, if you operate on a 2-qubit state, creating a tensor product out of these two, out of your knot and identity. And we'll look at how we can create a tensor product in a moment. But that means anytime you have a multiple qubit states or multi-qubit state and you want to do certain things, so execute gates on only a couple of these, then you will need the identity transformation for each of those that you want to leave alone. That's just a mathematical formalism, how we write that down. And that's why we need the identity transformation here. So X is unitary and is therefore an allowed transformation, as we can see, because this multiplication, a complex conjugate transpose times itself, or times the original transformation, gives you back identity. Now, the unitary transformations are always reversible. That's an important fact. And only reversible functions can be implemented. So as we said before, quantum computing and quantum physics is reversible. So apply the same transformation to a state twice, and you will get back the original state. That's how you can check if your transformation is valid, combined with the other checks that we already talked about. So why are only unitary transformations allowed? The key lies in the way the inner product transforms. So if we consider a state psi prime, which is the result of executing a unitary on a state psi, then we must have that the inner product gives 1. So let's say I'll just give you an example with basis vectors here. For the state 0, the ket vector looks like that, and the rho vector, which is also the complex conjugate, for complex numbers, if you look at the amplitudes, is given by the rho vector of this original ket state, okay? So in this one sums or gives you 1 if you execute the multiplication. And of course this also must be true for the final state, for psi prime. And we therefore have, if we look down here, that psi prime, or the inner product of psi prime, is given by the complex conjugate, or start with the bra vector here, and the complex conjugate transpose of your original transformation, then your original transformation applied to the state psi. So if we just distinguish here, let me make that line here, then the bra vector, you always execute that complex conjugate transpose on that vector here, and on the ket vector you take the original transformation, okay, which then results into this one here. So why is that? We remember if we look at that multiplication here, then this result of this must be identity, okay? So unitary transformations are rotations in state space which preserve the length of the state vector, so the inner product. So that means your states, so say we have the state 1, 0, after doing your unit or applying your unitary transformation, it must still be 1, 0. It can't be 2, 0. So it must preserve unitarity, because otherwise these states wouldn't be meaningful anymore, right? And the fourth and last postulate in quantum theory is the state space of a composite physical system is the tensor product of the state spaces of the component systems. What does that mean? So that means that there are two parts to this, so which is determining the basis for the composite system and determining the components of the state vector. So assuming we have two independent state spaces with orthonormal bases, respectively, so which we have here given by states u and v, then we bring this together to form a single composite system. So very much like we briefly talked about combining the knot and the identity transformation before. Then the basis states for the composite system are defined as, given by the state w here, u and the tensor product of u and v for every combination of u and v. And you may see different ways of notation. So sometimes people write it that way, sometimes that way. We'll continue to write it that way here, but it's all the same. So as I said before, this is very important. What this is, the bracket system, or the bracket way of writing things down, is just a description of operations and state vectors. Really, you can give it any name that you want, but there are some conventions, such as, for example, describing the state vector 1, 0 with the state 0. Okay. So let's look at two qubit states now. So let's say we take two independent qubits. By the way, if you wonder why sometimes you'll see qubit written without a u and sometimes you'll find it written that way, this is because at the very beginning when I started working in quantum computing, I was very adamant about writing the word qubit like we have it here, which also the convention that David Mermin, who is quite famous in quantum computing, which David Mermin pushes forward. But now the convention that everyone adopts is writing it that way here. So sometimes I may just not have corrected it to this one here, but suffice to say, this is what everyone does right now. So let's say we take two independent qubits, each has the basis states 0 and 1, and the basis for the composite system is, so if you do the tensor product here, 0, 0, 0, 1, 1, 0, 1, 1. And we can try that out. So if we look at the state 0, 0 here, let's write that down. We have the state 1, 0, and we do a tensor product with the state 1, 0. And it just means we have to multiply everything with everything. So we do 1 times 1, giving us 1 here. Then we do 1 times 0, giving us 0. We have 0 times 1 giving us 0, and we have 0 times 0 giving us 0. Okay, so which equals the state 0, 0 in that case. And the same is true for the other states here, of course. So maybe let's do one other example. If we have the state 0, 1, then we start with 1, 0, do the tensor product with 0, 1, and we have 1 times 0, 0, we have 1 times 1, 0 times 0, and 0 times 1, which is 0, 1. And please excuse my handwriting, I know it's not the best. So the basis states, to sum this up, contains all the possible combinations of the single qubit states. And measuring the state of the composite system can therefore yield 0, 0, 0, 1, 1, 1, or 1, 0, as we might expect. So each of these, if it's in a superposition, each of these here is associated with a certain probability amplitude, and what you get depends on mostly on the probability amplitudes and how they're distributed over these states. Only condition, as we remember, is the squared amplitudes must sum to unity. What are the coefficients of the basis state in the state vector? So if we consider two independent states, then this is what we had before. So for each of the basis state vectors, we have one probability amplitude and sum this up, okay? And the composite system, the tensor product, is formed as follows. So as we just described before, the basis states are ij, in our case 0, 0, 0, 1, 1, 0, 1, 1, and the state of the composite system can then be written as the sum of these amplitudes and the basis states. So it's really quite straightforward. It's very, it's just what we just did before. So let's look at some other examples here. So if we have two independent qubits in the states, so the one that we already saw before with 1 over the square root of 3 is a sort of probability amplitude associated with the state 0, and a square root of 2/3 associated with the state 1. And we have a second state, psi sub 2 here, with 1 over the square root of 5 for the state 0, and we have 2 over the square root of 5 for the state 1. And the basis for these composite systems, because we're still operating on single qubit states here, we want to combine it to 2 qubit state. So the basis for the composite system is this. So our possible 2 qubit states. And the very general state, without talking about amplitudes specifically, is the amplitude sub 0, 0 associated with the state 0, 0, sub 0, 1 associated with the state 0, 1, and so on. And we simply multiply the coefficients in the single qubit states in the appropriate way. So if we look at what we just did before, we have, or let me write that down here on the top, we have for 0, 0, we have 1 over the square root of 3. Then we have, for the second one, 2/3 square root. So this is my first one, okay? And now if I execute that tensor product with 1 over the square root of 5 and 2 over the square root of 5, then what I get is, so I do 1 over the square root of 3 times 1 over the square root of 5 for a 0, 0. This is what we see here. And then I do 1 over the square root of 3 times 2 over the square root of 5, which is a sub 0, 1, which is given by that one. And then I do square root of 2/3 times 1 over the square root of 5, which is a sub 1, 0. And my a sub 1, 1 is given by 2 2/3, square root of 2/3 times 2 over the square root of 5. And if we execute that, then we get that new compound state, which is still normalized. So that's very important. Okay, if the two single qubit states are normalized, then executing the tensor product of these will also be normalized. So result in a normalized state. And last not least, so to conclude the postulates, so one additional remark here is that sometimes when we're dealing with multiple qubits, we're dealing with entangled qubits. So entanglement means that we have a correlation that exists between n qubits. Let's say we have two qubits, qubits A and B. If I entangle these two qubits, that means if I do something to qubit A, it will also affect the state of qubit B. And that means that these do not exist as independent systems anymore. So anytime, even if you apply identity to the second one, so anytime I do something to entangled qubits, to two entangled qubits, then this changes. So if I apply one transformation to one qubit, this also changes the state of the second one. Okay? And it's often very convenient to describe one qubit or a group of qubits by density matrix or a mixed state. And so in that case, if you hear density matrix or mixed state, we think about entangled states. We'll learn more about that in a bit. This just summarizes what I just said. So not all composite systems can be made from independent systems. So if a composite system is not separable anymore, and you can't treat it as single qubit states anymore. So look at that state that we have here, a 2 qubit state, 1 over the square root of 2 for 0, 0, and also 0, 1. If you look at the bottom, at the top here, if we write that in vectorial form again, then this would mean this. So I have 1 over square root of 2 associated with 1, 0, 0, and I have 1 over the square root of 2 associated with 0, 0, 0, 1. Okay? And if you now try it out, this example here, so there are no two states with these amplitudes. So let's say these are example states, A and B, such that you can execute a tensor product between them that gives you an entangled state. So why is that? If we look at that, for two states with, let's write that down here, A0, A1, and we have B0, B1. That would mean, because here in the middle we have two zeros, that would mean that either A sub 1, B sub 0, and also A sub 0 and B sub 1 must equal 0, because otherwise we wouldn't get these zeros here in between for the states 0, 1, 0, 0 and 0, 0, 1, 0. But this can only be true if one of these, so if A sub 1 or B sub 0 in that case, or A sub 0 and B sub 1 equals 0. This must mean that at least one of A sub 0, B sub 0, and A sub 1, B sub 1 must also be 0. So you see, it's not possible to create such a state by a tensor product of single qubit states. So therefore, it is an entangled state. And how you create an entangled state, we'll see. So that's also coming in one of the next lectures. Okay, entanglement just to add to that, is a pure quantum effect, so there is no classical counterpart. There's also no classical counterpart for superposition, and there is no classical counterpart for tunneling, and we'll encounter it again when we discuss quantum teleportation. It's required to execute quantum teleportation. So, to conclude this, let's look at two different kinds of systems. So one is a classical probabilistic information processing device, and the other one is a quantum information processing device. And let's look at these devices from the perspective of the postulates that we just worked through. Let's start with a classical device. So what are computers? So you may have heard about some of or all of these different ways of implementing a computing model, such as a Turing machine, lambda calculus, von Neumann architecture. And let's assume it's just a system with some internal degrees of freedom, the memory, and rules for how this change over time. So for the first one, the rule one, the configuration description. So the internal memory is described by a finite alphabet of symbols. And these symbols label the different configurations of the system. System can only be in one configuration at a time. So if you run a classical computation, you operate on a string of bits, but at any given point in time, it can only assume one certain configuration. So it can only be at one certain configuration at a time. And we talk about configurations and a configuration ment. So a configuration ment means that there is a probability of 0.5 that as a system, this is in one of two possible configurations. So the description of the configuration is not the configuration itself. Okay, so this is also what we had before when we talked about quantum states, where we had the bracket notation and which is just a description. No, it's not only just a description, it acts as a description of vectors, but it's also easier to execute transformations. So we'll learn about that too. Let's see. So in general, our description of the information processing system will be a set of probabilities that the machine will be in one of these particular configurations at a given time. We denote these probabilities by a vector of probabilities, which we see here on the bottom, okay? Which is, in that case, p sub 0, which again is the probability of the state of the system being in that state. So for our basis vector description, it means p sub 0 that the system is in the configuration 1 and followed by zeros. We'll note, we had that one already. So we can choose some arbitrary order of the n configurations of the machine and call them 0, 1, etc. up to n minus 1, which we just did here on the bottom. And we summarize these probabilities, so as we just said, as a vector. One condition that we also have is that the probabilities must be positive. So p sub I, which means one specific probability, must be greater than or equal to 0, and they must sum up to unity. That's also a condition that we take over for probabilistic systems, and also a condition for the probability amplitudes that we have in quantum systems. So let's assume we have a system which can be in 3 possible configurations. And right now, when we look at that system, is being in configuration 0, which is this top configuration here, with a probability of 30%. And in configuration 1, here, with a probability of 70%, and in configuration 2, with 0 probability. And the probabilities here are represented or given in that vector. Okay. Now we look at the evolution. After being able to describe the system, we look at how it evolves over time. So the way in which our description evolves requires this. So given that the system is in a configuration I, so one of the specific basis configurations that we looked at before, the system in a given time step can evolve into any of the other configurations with a certain probability. And to describe such a probabilistic evolution, we need to specify these probabilities. I think it's always more useful when we look at an example. So here, this is just the summary, the probabilities. A sub j, I must be greater or equal 0, and must sum to unity, as we had before. So what we see here, P's are a vector of n probabilities. So here we have the ith configuration, the ith probability or component, and then we will end up with a new vector after applying or doing the evolution of that system. So let's see how that goes. Let me skip that one. So suppose that we have a two configuration machine, which is described by probability vector P of 40 and 60%. So T denotes transpose to make it a row vector here. And now suppose the evolution of the machine is such that if the machine is in the configuration 0, it stays the same with probability of 40%, and it flips to 1 with probability of 60%. And if the machine right now is in the configuration 1, it remains in configuration 1. So then the matrix describing this is given by that here. So we have these two configurations here on the right. We have our probabilities here. We're not talking about probability amplitudes in that case. We're talking about probabilities specifically because we're in a classical system. Then we said, if we just go back here, then we said it stays the same with probability 0.4 if it is already in the configuration 0, and it flips to 1 with probability 0.6 if the configuration is 0, and it stays in configuration if it is already in configuration 1. So what we do now is we apply our probability vector, the one that we just talked about, and we execute that multiplication. So we have 0 times 0.4 times 0.4 plus 0 times 0.6, which gives 0.16. We have 0.6 times 0.4, and we have plus 1 times 0.6, which gives this result vector here, so 0.84 for the second probability. So the configuration of that system after the evolution is given by this probability vector. Okay. Now let's look at the third rule. What happens when we measure the device? The system is always in some particular configuration, but our description of the system is just a vector of probabilities. Thereupon, it's possible to calculate the probability that the system is in a particular configuration. Immediately after such a measurement, our description of the probability will collapse onto whatever the outcome is that we measure. Collapse means that all the rich probabilities, like in the quantum system that we had before, are gone. But we will end up with a definite state. So again, if we just go back to this example here, let's say the probability of measuring the system in state 1 is a lot higher, then what we will get as a result here is 0, 1, which is the state 1 in that case, but it means all our probabilities, this rich information that we had here, is gone. We'll end up with a definite state. And for composite systems, so the rule 4, what happens when we bring two of these devices together? So let's assume we have two machines with n and m configurations, and we allow them to communicate back and forth and manipulate their configurations. And it's possible to make a new machine, which is exactly like a probabilistic information processing device, but with m configurations. And this rule 4, the composite systems, as we learned before, is about the relationship between the original and the new machine. And we do that by means of a tensor product. So here is the formalism as to how you write that down. But let's look at an example. I think that always makes things easier. If we have two machines, and there you have the probability for the first machine in state 0, and the first machine being in state 1 with 1 times p sub 1 here, and the same for the second machine, so that it is in state 0 is given by probability q sub 1, and that is in the first state is given by 1 minus q sub 1, of course. So if we do the tensor product again, like we did before, and just with probabilities here, we have p sub 1 times q sub 1, and we have p sub 1 times 1 minus q sub 1, 1 minus p sub 1 times q sub 1, and 1 minus p sub 1 times 1 minus q sub 1. So this is the executed tensor product here, and gives you the state of the combined system. Description of the combined system, sorry. And for the basis states, that means this probability p sub 1, q sub 1 is associated with the state 0, 0. This one here is the second one is associated with 0, 1, and so on. Okay. And let's look at a specific example. Continue to look at this example that we mentioned before, where we have entangled system so you may try it out. If you can find a tensor product that two 1-qubit systems or 1-bit systems that gives you that combined state here. So this configuration is denoted, so if you have state 0, 0 associated with 1/2 and 1, 1 associated with half, is denoted by this vector here. So remember, state 0, 0, as we said before, is just 1, 0, 0, 0. State, so in that case, state 0, 1 is given by this one here, and we have the state 1, 0, which is given by that one here, and then we have the state 1, 1, which is given by that one here. Okay. And since we're now looking at the state 1, 1, which is this one here, state 0, 0, which is this one here, then if each of these have the probability 1/2, and the middle ones have the probability 0, the vector is given by this one here that we see here on the bottom. And as we said, there is no way of expressing it as a tensor product of these two states P and Q. So we say the machine state is correlated, but for quantum computing, remember it's entanglement, but that's something different. So entanglement refers to stronger than normal correlation, and purely quantum. And of course, we can define a tensor product for matrices as well. So if we have the two matrices A and B given with so A given by A sub 1, 1 until A sub 2, 2, and the same for B given by B sub 1, 1 up to B sub 2, 2. Then if we create a tensor product out of these, it's again every element by every element is a bigger matrix. So two-dimensional matrices, tensor product, if you create one out of these, will result in one 4-dimensional matrix. Okay, and this could be one matrix that you apply to a 2-bit state, such as this one here. Now, let's look at a quantum information processing device. So, very similar path to a way how we look at this, again starting by the configuration description. The major difference to a probabilistic system is that the system is not described by a set of probabilities, but given by a vector of probability amplitudes. We had that before already. So we describe our system with n configurations by a unit vector in the space of C power of n. So that means it's a complex vector. So we have complex probability amplitudes. So, and the complex numbers, as you remember, this is one example for a complex number, is a plus bi, where you have a and b being an element of the real numbers, and I squared equals -1, so a complex number. Okay. The configuration description of the machine is a vector of these n complex numbers, so that didn't change. You still have an n component vector that holds, in that case, the probability amplitudes, not the probabilities. It's a unit vector, so it must fulfill that the inner product equals 1. Or in component notation, in that case, you have the complex conjugate transpose here, as we just mentioned before. And then you take the modulus equals 1. So the complex conjugate, just to sum that up here, is the sign change of the complex part that you have, okay? So if we compare these two, the configuration description of classical and quantum systems, then you have n configurations. You have n configurations both classically and quantumly. In a classical system, you have a vector of probabilities compared to a vector of amplitudes in the quantum system. You have the probabilities being out of so an n component vector, which is each of which is a real number, whereas in the amplitudes, you take your probability amplitudes out of the complex number space. And the probabilities in the classical systems must sum to 1 on the modulus in the quantum system. So taking the complex conjugate times the original complex number, and you sum that up for all the components, then it must also give you 1. So here it's just summarized again. The probability that you observe, or that we observe the system in the configuration I, is given by the modulus squared. So we see in our table above that the prescription that V is a unit vector, as we just said, and there's really a requirement that these numbers are probabilities. So it's always positive, that's also important, and must sum to unity. So remember that one. So usually we don't call the vector with probability amplitudes the vector of amplitudes. So we just call it as description of the wave function or a quantum state. Okay. And now if we just look at some examples, or one example here, I think that helps again. So a possible description of the configuration of our system is given by the wave function 1 over square root of 2 and I over square root of 2. So you can check that this is a unit vector easily. So if we just square it, so here 1 over square root of 2 of course gives you 1/2. And since we have the absolute value of I squared is, as remember, -1. So if the absolute value is +1, and we remove the square root here because we squared out 2, so then again it sums to 1/2 plus 1/2 equals 1. So if we measure the system, we will find that the probability of finding it in either configuration is 1/2. Now let's look at the second rule. So the probabilistic device was described by a stochastic matrix, and the matrix now must be unitary. So as we learned before in quantum theory, that requires that we use unitary operations, and so the matrix that we use for evolving our system must also be unitary. So again, if we have an n configuration system, then our wave function will be described by a unitary matrix of n times n. If the original vector is v, and then we evolve to the unitary matrix u, then the new vector v prime is given by the unitary transformation applied to v, the original state. Or in terms of components, where you see v sub j prime equals the sum over all I of u ji u sub ji times v sub ji. The requirement for our probabilistic machine was that the evolution matrix to be stochastic because it required that the system respects the fact that we're evolving probability vectors. But now we're evolving amplitudes, and the complex vectors that we evolve are required to be unit vectors. We don't want this to change under the evolution, and this leads to the requirement that our evolution matrix must be unitary. And the unitary matrix, as we learned before, is one whose complex conjugate transpose is also its inverse. So if you take the complex conjugate transpose of your transformation and you multiply it with the original transformation, it must give you back identity. So we have down here, we have the equation again. So again, remember the star here is the complex conjugate transpose and the complex conjugate, and then you flip the components here. You get the complex conjugate transpose. So let's look at an example that makes things easier again. What you see here is a matrix that is unitary, but how do we know? We check. So the first thing that you do is you do its complex conjugate. Okay, so you look at all the complex numbers that you find in that matrix, which are these two, and you switch the signs, because that's what you do when you do complex conjugation. You just switch the signs of the complex components. And it's a conjugate transpose once you also do its transposition. So in that case, what happens is that this one moves up here and this one moves down here. Okay, so the resulting matrix equals this one here, which is not identical to that one over here, but let's check further. So we now take the complex conjugate transpose, multiply it by the original matrix. So we do that we do that multiplication. So the 1 over the square root of 2 times 1 over the square root of 2. So this one here will be the first one plus I over the square root of 2 times minus I over the square root of 2 gives you the first component. And so on. So you can do that yourself. And the result is, as you see, identity. So identity, that's not checked. So it is a unitary matrix. And let's assume we have a system given by the wave function, so equally distributed superposition, so 1 over the square root of 2. And we evolve this wave function according to the above unitary evolution. Then the new wave function will be given by this state here, so 1, 0. So if you do that evolution again, then you get back the original state, which is this one here. So you may want to try it out, but this is one of the requirements that we have reversible transformations. Okay. Now let's look at the third one, measurement. So when we measure our quantum system, which is described by the quantum state V, we'll find the configuration I with probability of modulo squared for I. Okay. Now, how do we update the description of the system after this measurement? So if we made a measurement and found the configuration I, the new amplitudes of the quantum systems must satisfy the condition that V sub I prime is delta ij, so which means there is only one non-zero amplitude that is equal to unity. Okay, so you may have seen that before. And in quantum physics, so evolving a system in time is a physical process, and also the measurement is a physical process, which means that there is a certain configuration of physical systems which we arrange to carry out a unitary evolution, and a different configuration which we arrange to perform a measurement. And Anytime we talk about measurement here in quantum computing, we talk about measurement in the computational basis. So, which, for example, in a 1-qubit state are again 1, 0, 0, 1. That's the computational basis. Let's look at an example. So suppose our quantum device has a quantum state, V, which is given by square root of 3 over 2 for configuration 0. And for configuration 1, it's 1/2. And again, we look at the transpose here. And the probability of measuring the system and finding it in configuration 0 is given by the absolute value of square root of 3 over 2 squared. And if this happens, so if you end up with this first configuration, then as you can see, the final state is given by 1, 0, meaning of the 0th configuration, which means that this probability here and this probability here, they're gone. So all this rich superposition information that you had before is gone. It's not there anymore. And now, if we combine systems, so remember how we did that before, it's exactly the same here. So I will skip that part. This is just the formalism. But in the end, how you do it is also by taking a tensor product of a basis, in that case here. So we had E sub I and F sub I here, but it works exactly the same. Okay, to conclude this lecture, I brought a quiz, and you'll find the solutions to this quiz also in this presentation. But please try to work through that on your own. It will also be very helpful for the exam. If we look at this first one, so remembering that unitary operators obey, so the complex conjugate transpose of the original operator times the original operator equals I, so identity. Check, please, which of the following operators is unitary. So for a second one, you have a couple of states given, and now construct the composite states out of these. Okay. Whoops, that were solutions already. You haven't seen that. Then please try these out, and we'll continue in the next lecture. So thank you very much for listening in, and have a nice remaining day.